Hello, I am Saman Razavi, and in this short pre-recorded AGU talk, I'm going to look at differences between deep learning and process-based modeling. The former is a data-driven modeling process using a modern class of artificial neural networks, while the latter is about modeling based on the knowledge-based and the known mechanics of real-world systems. An overarching question here is if and possibly how these two fundamentally different modeling paradigms may be reconcilable. Let's begin with a fairly simple and typical modeling experiment. The objective of this experiment was to model the hydrologic system of the Oldman River watershed in Alberta, Canada, with an area of almost 1,500 square kilometers. On average, this watershed receives about 600 millimeters of precipitation, rainfall plus snowfall annually. It has a long-term average temperature of 2.2 degrees Celsius and generates about 12 cubic meters per second of river flow. This is a snow-dominated watershed in cold alpine regions of Canada with about 30 years of data. To model this system, standard long short-term memory or LSTM neural network was chosen as a state-of-the-art deep learning model that accounts for time dependency and memory. The LSTM configuration here had 166 calibration parameters. Those parameters by nature do not have any physical meaning or range of feasibility. For benchmarking purposes, the HBV model, which is a classic and well-established hydrologic model with only 12 parameters, was used as well. Each of these parameters has a physical interpretation and a physically justified feasible range. These two models were trained or calibrated on the exact same data, with daily precipitation and temperature as their inputs and the daily concurrent flow as their output. Now let's look at the performance of the two models in calibration and validation. To ensure a robust comparison and to account for possible variability of model performance, 5 independent replicates of calibration experiment with different initial random seeds were conducted. The error function used in calibration and validation is Sutcliffe efficiency or NSE. The higher the NSE, the better the model performance, with a value of 1 indicating a perfect fit. Based on the results in calibration, the superiority of LSTM over HBV is significant in terms of goodness of fit to stream flow. And in validation as well, LSTM apparently outperforms HBV across all replicates. Consistent with these results, the hydrologic modeling literature is full of such conclusions that neural networks are superior to process-based models in both calibration and validation. So, is this the end of story and this talk? Perhaps not. The standard practice for validation of a model, as done here, is to test its performance in terms of reproducing some historical record not seen during model calibration, a process typically called out-of-sample prediction. But a known but often neglected issue is that this so-called model validation is inherently partial. Strong assumption in this type of validation is that the conditions under which the model will be used will be similar to the conditions under which the model has been developed and calibrated. The intriguing fact is we already know that this stationary assumption may not hold, but this standard model validation practice has arguably remained unchanged. Let's dive deeper into the notion of out-of-sample prediction, and instead of the standard practice, let's compare the two models in true out-of-sample prediction by a stress test approach using a what-if scenario question. The question of choosing here is how the system would behave if the average temperature warmed by 2 degrees Celsius while everything else remained the same. To assess this merely hypothetical scenario, both calibrated models were fed a new temperature time series obtained by adding 2 degrees Celsius to all temperature values. So the average temperature rose from 2.2 degrees Celsius to 4.2 degrees Celsius. These new synthetic inputs roughly provide a picture of what might happen in this watershed under global warming. I should say though that the rather simplistic approach taken here for generating a hypothetical scenario is for demonstration only, and the state of the art for generating such hypothetical scenarios is much more advanced. A common policy question for hydrologists using such scenarios, particularly in Canada, is how seasonality of flows might change under warming in terms of both the magnitude and timing of flows. So first, let's check the consistency of simulated seasonality for the historical period. The red envelope shows the response of LSTM across the 5 replicates, while the blue envelope shows the performance of HBV across the 5 replicates. Both models generally follow the observed seasonality, but the range provided by the LSTM model is generally narrower and better encapsulates observations in both low and high flows. And now let's check out the hypothetical scenario. Again, the red envelope is the result by LSTM and the blue envelope is the result by HBV. Apparently, under the new conditions, the two models show distinct behaviors. According to LSTM, peak summer flows would decline by about 25% on average, and the time of the peak would shift backward by about a week, from the beginning of June to a time in the 4th week of May. But according to HBV, the changes would be more pronounced. The peak flows would decline by about 35%, and the flows might show two modes, the larger at the beginning of May and the other in mid-June. Now, given the big differences, the question is, what model should we trust? Which one gives a more credible picture under the truly new conditions? The intent here is not to give a specific answer to this question, but to draw your attention to a fundamental issue, that is the large divergence in the extrapolative behavior between models that produce comparable results in standard auto-sample prediction. In the following, I will try to address this issue across two fronts, one being about embracing the value of domain knowledge and the other about setting the model purpose up front. True out-of-sample prediction is nothing but extrapolation, which is a reality that many predictive models nowadays must face because of non-stationarity in climate and the environment. Any purely regression-type model, including those arising from deep learning, would be disadvantaged in extrapolation, as by definition, extrapolation would require working in parts of the problem space for which they have not received any information. But what does the domain knowledge offer when it comes to extrapolation? The answer is a set of principles modulated via conservation laws around mass, energy, and momentum, and process parameterization, which represent our perceptions of how two or more variables might be related. These principles are typically built-in process-based models, but deep learning by itself is unable to account for them. For example, the continuity equation in the typical deep learning models do not hold, and water can be falsely introduced or lost in the course of simulation. The knowledge base also includes information about known causal relationships, such as monotonicity and rates. For example, we know that the relationship between melt rate and available heat is monotonic, that is, more heat causes a higher melt rate. We also have some rough estimate of the feasible range of the rate of change in one with respect to the other. But if you want to learn everything about these purely from data from a given case study, you may misinfer them because of noise in data or sparsity in data. Another type of knowledge is about feedback mechanisms in real-world systems. For example, consider a coupled water vegetation system in which precipitation, available soil moisture, and plant biomass interact in complex time-dependent ways, even at times creating positive feedbacks that stabilize the system's behavior. But deep learning models are often unable to account explicitly, perhaps even implicitly, for such long-term dynamics. If a particular dynamical behavior is present in training data, then deep learning can capture that behavior. But it has no explicit mechanism to represent that dynamical behavior under perturbed conditions beyond what has been recorded in the training data. The bottom line is, if a model is equipped with the knowledge base, it would be less prone to generating spurious behaviors in true out-of-sample prediction. Therefore, many domain experts may be inclined to trust process-based models as their behavior is more constrained by physical laws with known limits of validity. We also need to carefully ponder about the modeling purpose for a given problem before getting into the design of a modeling experiment. The modeling purposes may be viewed under three general categories, namely nowcasting and forecasting, scenario analysis, and diagnostic learning. The first aims to look into now or foreseeable future and predict what will happen, for example, in a local or regional weather system. This directly supports real-time operation and management at different levels, from individual citizens to local, regional, or global institutions. The second, however, takes a what-if view of the future and aims to answer how the system might respond under new or altered conditions, such as climate or land use change. Thus, it supports long-term decisions pertaining to adaptation to change and building resilience in human-controlled systems. Conversely, the third is about looking backward by using models to simulate the past and present behavior of a system so as to answer why that system behaves as it does. This supports developing and testing new theories and hypotheses, thereby extending our process understanding and the knowledge base. In other words, diagnostic learning is about exploring causations and attributions of observed variability to controlling factors. For example, to explain the observed sea level rise in the past decades. So, how would the typical deep learning or machine learning in general do with respect to each of these modeling purposes? Machine learning is expected to perform well in nowcasting and forecasting, particularly when the underlying real-world system remains structurally unchanged in the forecasting horizon of interest. However, it can become handicapped or unreliable in scenario analysis if a scenario requires extrapolating well beyond data use to constrain the model, or is about a structural change in the underlying system, for example through human interventions. In such cases, the correlational structure of variables empirically identified by machine learning may not hold under new conditions. Lastly, machine learning, particularly deep learning models, because of their connectionist nature, may arguably be of limited help for diagnostic learning because they are not essentially built for system identification. In other words, it is typically non-trivial to compartmentalize a deep learning model and attribute its parts to the components of the system being modeled. So if I want to leave you with a message, it would be that more work is needed to bridge the knowledge base and deep learning in light of the intended modeling objectives. For more on this message, you may refer to the resources shown on the screen. Thank you very much.